In this video I'm going to be talking about trees. Now trees is something which comes from discrete maths, and you may be thinking, well hang on, we're doing a computational unit here, why are we starting to use trees? And the reason for that is that the mathematician John Butcher sort of discovered that there's a much easier way in which we can derive Runge-Kutta methods using trees as in the normal traditional methods, which use expansions and bivariate Taylor series. So that's what we're going to be looking at now. So we're going to be looking at trees. Now, obviously the sort of trees we're going to be looking at is not the ones which you see in the parks. So we're going to be talking about mathematical trees. Now, a tree is a graph. And remember that graphs are simply sets of nodes or vertices connected by edges. So a tree is a graph where any two vertices are connected by exactly one path. So in other words, there are no two ways to get from one vertex to another. And here we've got a few conditions for whether a graph G is a tree. So G is connected, which means all nodes in the graph it has to be possible to walk a path from one node to all other nodes. G has no cycles, so a path starts and ends. A path cannot start and end at the same vertex. And a cycle is formed by adding any edge to G. So if you have a tree and if you add any edge, that turns it into a cycle, which means it's not a tree. If we remove any edge from a tree, then it is disconnected. And if our tree has n vertices, then it must have n minus 1 edges. And perhaps the most important one for us is a tree is known as a rooted tree, where a special node is singled out, and that's known as a root node. And rooted trees are usually represented with the root vertex drawn at the bottom. Okay, so that's a few conditions for a tree. And this is one example of a rooted tree. So here we can see we have how many nodes have we got here? Just count them up. We've got 7 nodes, and this is a tree because if we look at the previous conditions, all nodes are connected. There are no cycles in this tree. There are 7 nodes, and there are 6 edges, etc., etc. So this is a rooted tree, and what we've done here is we've singled out this node at the bottom. Now this is our root node. Okay. Now, when we're dealing with trees, we don't always want to draw out a tree like this. It's much easier sometimes to deal with notation. So what I'm going to do now is introduce what we call tree notation. We define tau, so Greek letter character tau, as a tree with a single node. Okay, it doesn't look much like a tree, but this is a tree. So if we've got a tree with one node, 0 edges, we refer to that as tau. And we refer to a rooted tree T, so T is the name of our rooted tree, using this notation. So here we have square brackets. Okay, so that says we have a rooted tree, and within the square brackets we got lots of subtrees. So T1 is another rooted tree, T2 is another rooted tree, etc. So our tree T is formed by connecting all of these subtrees to our root node. Okay, and the root node tau. If T1, T2, etc. are all different or distinct, and let's say T1 occurs K1 times, so let's say we have K1 lots of T1, which is connected to our root node, we simplify this by using superscripts. So this T1 superscript K1 means that we have K1 lots of the tree T1 connected to the root node. Okay, so that's the tree notation. So it can be quite difficult just without sort of any sort of reference to diagrams. So here we've got an example. So here we have our tree with 7 nodes, 6 edges, and we have the root node here. So if we look at the root node, this root node has 3 children. So we have 3 other rooted trees stemming from the root node. Our first rooted tree is simply a node, a single node, because that doesn't have any children. Our second rooted tree is this tree here. So this is our root node of the second rooted tree, and that root node is connected to our root node of T. And finally, our third tree, we've got a tree with a root node and a single leaf node or child node. Okay, so here we have three rooted trees connected to our root. So T is the whole tree, and we have three subtrees. Okay, so if we were to represent these subtrees in tree notation, the first one's easy. We just have a single node, so that's just the letter tau. The second tree, we have a rooted tree. So we have another set of square brackets, you can see there, as represented by my cursor. Now, this tree here, we have two trees connected to our root node. These two trees happen just to be the character tau, and it's sorry about that. So we have, where was I? Yes, we have two trees connected to our root node, and these two trees don't have any children, any leaf nodes coming through them, so that's just the letter tau, but because there's two of them, we use the superscript 2. And our final tree, okay, it does have we do have a child node coming off a root node, so that's denoted by, so we have the square brackets, and our root node is simply tau. So this here is a rooted tree notation of this tree here. Okay, it does take a bit of getting used to this new notation, but if you sort of break it down, it does get easy, and we'll be looking at several examples in the webinars. Okay, I'm going to go on to talk about some properties of trees. So for these properties will be used when we start dealing with the derivation of Runge-Kutta methods. So the first property we're going to be looking at is the order of a rooted tree, and this is denoted by RT. So remember, T is the name of our tree, so RT is the order, and this is simply the number of vertices in T. Okay, and it's calculated by using the following recursive relation. So the order of a tree with a single node in is obviously 1. Okay, so the order of a rooted tree is going to be 1, which accounts for the root node plus the sum of the orders of all subtrees multiplied by the number of times that each subtree appears. Okay, so this might look quite complicated. It's a recursive relation, so we have to do a number of steps to actually calculate what the order is. Okay, so for example, here we've got our an example tree. Okay, so let's have a look at the tree notation for this. So we have a root node, okay, and connected to the root node we have two subtrees. The first subtree does have children, so we denote that by a set of square brackets, and each of these children is simply a single node, and that is repeated, so we have tau superscript 2, and our second subtree does have a child node, so that's represented by the square brackets there, and this has simply got a single node here, which is just a single tau. So this is our tree notation for this example tree. So if we apply this recursive relation, so we have 1 plus, now this tree here only, or I should say this tree here only appears once, so we have k1 is 1, which I've actually just not included it, and that's times the order of the subtree, and the subtree is a rooted tree with two child nodes. And the second tree, okay, so this is this tree here, so this is it appears once, and so that's 1 times the order of that tree. Okay, so now we're dealing with this. So if I calculate the order of this tree using the same relation, so this is where the recursiveness comes in. We have 1 for the root node, so that's accounted for that node, plus now the 2, because this tau is repeated, multiplied by the order of the single node tau. So that bracket there is this equation applied to this tree here, and doing the same for the second tree, we have 1 and the child node here only appears once, so it's 1 times the order of tau. Now the order of tau is just 1, so we've got 1 plus 2 times 1, which is 1 plus 2 obviously, and 1 plus 1 here, and this gives us 6. Okay, so you could also calculate this by simply calculating the number of nodes here, but where's the fun in that? Okay, the next property we're going to be looking at is the symmetry of a rooted tree. Now symmetry is denoted by sigma t, and it's quite, if we want to use grand words, it's the order of the automorphism group of T that can be calculated using the following relation. So in other words, it's how many trees can, or how many ways can a tree be represented by swapping various nodes. Okay, so the symmetry of tau, so if you just got a tree with a single node, well, that can only be represented one way. The symmetry of a rooted tree is, this time it's a product. Okay, so product of all subtrees multiplied by the number of times they occur factorial and to the power of the number of times they occur. Okay, so using the same example as before. Okay, so this tree here, that appears once, so we have 1 factorial times the symmetry of the tree to the power 1, and this tree appears again once, so it's 1 factorial times the symmetry of that tree to the power 1. Okay, so now what we're going to be looking at is we're going to be looking at this symmetry. Okay, so the symmetry of this subtree here. Right, so what we have is this tau appears twice, so k, in our case ki is 2, so we have 2 factorial times the symmetry of each of those subtrees. So the subtree is just tau to the power k, which in this case is 2. For the second symmetry one, there we are. Okay, so tau only appears once, so it's 1 factorial times the symmetry of tau to the power 1. Okay, so the symmetry of tau is just 1. So here we have, and 2 factorial is 2, so we have 2 times 1 squared plus 1 times 1 to the power 1, so this is 2. So this means this tree can be represented in 2 ways, and which will still give us the same tree, and those 2 ways are simply by swapping these 2 nodes here. Okay, and we're going to be looking at the density of a rooted tree. Okay, so density is denoted by gamma t, and again we have a recursive relation, so the density of a tree with a single node is 1, and the density of a rooted tree, well, that's the order of the rooted tree multiplied by this product. Okay, so here we have the densities of each subtree raised to the power of the number of times they occur. So again, using the same example, we previously calculated the order was 6. Okay, and we got 2 trees, so we got this first tree appears once, so that's raised to the power 1, and the second tree also only appears once, so that's raised to the power 1. Okay, so now if we apply this equation to calculate the density of this tree, okay, now the order of this subtree here is 3, and that's multiplied by the summation of each subtree from each child node. Okay, so because we've got a repeated node, that's gamma tau to the power 2. Okay, so that's that density calculated. Onto the second one. Okay, this is slightly easier. So we have, this is our second subtree. So we've got an order of 2, and because it's only got 1 child node here, we simply have gamma times tau to the power 1. Okay, now gamma tau is 1, so 3 times 1 squared, 6 times 3 times 1 squared times 2 times 1 squared, which is 36. Okay, so that's the density of that rooted tree. There is another way to calculate the density, somewhat easier. So that's if you do have the diagram of the tree drawn out. So what you can do is you can assign all the leaf vertices a value of 1, and all other vertices are the sum of the values of their immediate child vertices plus 1. And then the density is a product of all the values of the vertices. So here we have our same example tree before. So we start off by the leaf nodes, we assign a value of 1. For all other nodes, it's a product. It's a sum of their leaf node values plus 1. So 3. The reason why this is a value of 3 is because we've got 1 plus 1, which is sum of. So the sum of its child nodes is 2, but plus 1 gives us 3. And here, it's only got one child node of 1, but plus 1 gives us 2. The root node, it has child nodes with values 3 and 2, so add them together we get 5 plus 1 to get 6. Now you know if you've done it correctly because the root node should have a value of which is the same as the order of the tree. And then all you do is multiply all those values together, and that gives you the density of that tree. So that's just another way of doing it. Okay, the last thing we're going to be looking at is sort of number of ways in which a tree can be labelled. Now, the reason we're looking at this is important when we come to look at the derivation of Runge-Kutta methods. So I'm going to define alpha and beta. So alpha t is number of ways of labelling within an ordered set. Okay, so how many different ways can we label our tree T? And this is given by this relation, quite simple. So if you know the order, which is RT, so it's order factorial divided by the symmetry, sigma t, multiplied by the density, gamma t. So that will give us the number of ways in which we can label a tree. And that's within an ordered tree, so that's when we haven't moved anything, we haven't swapped any nodes. Beta t is the number of ways labelled within an unordered set. So this means we can swap nodes around, and this is simply the order of your tree factorial divided by the symmetry of the tree. So in our example, okay, so this is our example from before. This tree had an order of 6, symmetry of 2, and a density of 36. So 6 factorial divided by 2 times 36 gives us 10. And the beta t is simply order factorial divided by the symmetry. In this case, 6 factorial is 720, so that gives us 360.